We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.
There she is, NASA's Voyager 1, launched in 1977.
But that's just very small potatoes compared to what the Earth is involved with and knows about.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
One small step for man, one giant leap for mankind.
Greetings mga ka-spacers and welcome to this episode of Space, the Final Frontier. This is your ka-spacer, Professor Jun Cajigal. Now, Space, the Final Frontier is a series of online lectures that is designed to help inspire our students out there to love the sciences, especially astronomy. And for today's episode, we shall be focusing on the Space Shuttle, the end of an era. So if you have any questions or comments or reactions later during our online lecture, please feel free to type in your questions, your reactions, or your comments in our comment section below. So wag po kayong mahiya. and he would be very happy to answer all your questions and queries. So tara na mga ka-spacers, and let us study the Space Shuttle, the end of an era, and let us go where no man has gone before. Greetings mga ka-spacers! So for this episode, we shall study the Space Shuttle and its vital contributions to space exploration. Now, the Space Shuttle was officially known as the Space Transport System or STS. And did you know mga ka-spacers that the Space Shuttle was the most complex space vehicle design of its time? The Space Shuttle was the first reusable launch vehicle to reach orbit, but unfortunately mga ka-spacers, it failed to accomplish the intended goal of reducing launch costs to below those of expendable launch systems. But at any rate, the Space Shuttle was responsible for the construction of the International Space Station. So for this lecture, we will go into the details of the design of the Space Shuttle, its historical background, and some of its accomplishments, and some of the disasters that occurred during the Space Shuttle era. So to start our online lecture, let's take a look at the beginnings of the Space Shuttle. And did you know mga ka-spacers that the concept of the Space Shuttle started during the late 1930s? So in the late 1930s, the Nazis initiated the America Bomber Project. This is an effort to build an aircraft capable of taking off from Germany and dropping a bomb on the continental United States. A German named Eugen Sanger submitted proposals. Sanger's idea, developed with the mathematician Irene Brend, was a type of winged rocket called the Silber Vogel, which is the German term for silver bird. So mga ka-spacers, ang galing talaga ng Germans. So this guy by the name of Eugen Sanger really came up with this idea of a winged type rocket called the Silber Vogel. And this rocket, the Silber Vogel, would ascend to suborbital space and drop down into the stratosphere. At that point, the increasing air density would give the vehicle lift, bouncing to a higher altitude again. The process would repeat with the Silber Vogel, making the trip across the Atlantic in a series of leaps and bounds. So that was the idea of that rocket-powered plane designed by Eugen Sanger. Now, isn't that fascinating that the Germans were really ahead of their time? And as the 1950s were on, reusable shuttle-like space planes were increasingly viewed as the key to the nation's ability to access, explore, and exploit space. And this was realized by the pioneer rocket scientist Wernher von Braun. Wernher von Braun realized the importance of having shuttle-like space planes to access, explore, and exploit space. And in the so-called von Braun paradigm, space exploration according to Wernher von Braun should involve the following steps. Letter A, putting a human in space. Letter B, to develop a reusable spacecraft, making access to space cheaper and easier. Letter C, to use this vehicle to build a space station, and letter D, to inhabit the space station and employ it as a base from which to launch manned expeditions to the moon, to Mars, and beyond. So mga ka-spacers, isn't that fascinating that Wernher von Braun had already dreamt of building shuttle-like space planes in order to construct a space station. And this space station will be used as a base to which to launch manned expeditions to the moon, Mars, and beyond. And NASA took this vision of Wernher von Braun seriously. Alright, so NASA took this vision of von Braun to heart, using this as a roadmap when charting its course in the late 1950s. So that was the vision of Wernher von Braun. Really, Wernher von Braun was the architect behind the American space program. So if NASA had visions of space planes dancing in its head in the 1950s, why did the nation wait until 1972 to officially begin the shuttle program? So what do you think, mga ka-spacers? So the answer there was the space race. The space race intervened. That's why the shuttle program had to wait until 1972. So mga ka-spacers, it was Wernher von Braun who became instrumental in helping the Americans win the space race. Wernher von Braun was the architect behind Project Mercury, Project Gemini, and Project Apollo that led to the development of the mighty Saturn V rocket that carried the American astronauts to the moon. And after beating the Soviets to the moon, NASA needed some new goals. In early 1969, President Richard Nixon established a Space Task Group to help determine NASA's post-Apollo direction. And in September of that year, the group delivered its report, which recommended going back to the von Braun paradigm in some fashion. The shuttle, the space station, the manned moon trips, and finally, manned mission to Mars. So mga ka-spacers, it was the Space Task Group that recommended to President Nixon that they have to go back to the original vision of Wernher von Braun to develop a reusable space shuttle, to construct a space station, to continue their trips to the moon, and possibly plan a manned mission to Mars. But President Nixon was not pleased with that recommendation of the Space Task Group. The president thought that the idea, the plan, was too expensive for NASA's budget. So he zeroed in on a single aspect of the von Braun paradigm, ditching the others. And according to President Nixon himself, the one standalone thing that you can point to was the shuttle. So that's where NASA went. They started constructing the space shuttle. So NASA accepted the challenge and decided to develop the space shuttle. Now this decision to develop the space shuttle was a key shift in NASA's charter from space exploration to space utilization. In announcing the shuttle program to the nation on January 5, 1972, President Nixon stressed its practical benefits, saying that the space shuttle program could help the United States get into space frequently and relatively cheaply. Presumably, further advances would follow from this ability. So mga ka-spacers, before we continue with our discussion of the Space Shuttle, let's watch this interesting video on how Wernher von Braun came up with the idea of a reusable space shuttle. Okay mga ka-spacers, let's watch this.
To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Wernher von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
Now here's a model of my design for a four-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large, but the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these three additional rocket-powered sections. Here we have a cutaway drawing of our rocket showing the location of the fuel and the motors of each section. The first stage carries 1,060 tons of fuel, and its 29 motors will lift the entire weight of the ship vertically off the ground. The second stage has 8 motors and carries 155 tons of fuel. It will be dropped when its speed has reached 14,300 miles per hour. The next is our third stage, with only 1 rocket motor and 13 tons of fuel. The third stage gives the passenger section the final kick to attain the orbit. It will not be separated from the passenger section until just before the return flight. The third stage will be left in space, and a very small motor in the winged fourth stage will return the ship to the atmosphere so it can glide back to the base. If we were to start today on an organized and well-supported space program, I believe a practical passenger rocket could be built and tested within 10 years. Of course, it would be foolish to rush headlong into building a 4-stage rocket, man it with a crew, and attempt to fire it into an orbit without first following a step-by-step research and development program. Let's illustrate this with the help of a few pictures. First, we would design and build the 4th stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the 4th stage. This would also give the crew more and more training. Following that, the 3rd and 2nd stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights could be made up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge 1st stage. Then there would be no more test flights. When all the sections are joined together, the ship and its crew will be ready for man's first flight in space.
So mga ka-spacers, that's really interesting about how Wernher von Braun came up with the idea of a reusable space shuttle. Now, another crucial factor in the development of the space shuttle was the so-called lifting body aircraft. Now, what is a lifting body aircraft? Now, a lifting body aircraft is a fixed-wing aircraft or spacecraft configuration in which the body itself produces lift, in contrast to a flying wing, which is a wing with minimal or no conventional fuselage. A lifting body aircraft can be thought of as a fuselage with little or no conventional wing. In fact, this aircraft was featured as an introduction to the TV series $6 Million Man, wherein Steve Austin was a test pilot of one of those lifting body aircraft. So before we continue, mga ka-spacers, let's watch this interesting video about the lifting body aircraft. Alright mga ka-spacers, let's watch this.
Seen the space shuttle taking off, but most of us take its design for granted today. It wasn't too many years ago that this unusual design shape was considered impractical. That was until a resourceful engineer from NASA named Dale Reed began working on design shapes called lifting bodies, which would change the shape of reusable spacecraft. The lifting body concept evolved in the late 1950s as researchers considered alternatives to the simple ballistic design of space capsules. Many felt that astronauts should have a more sophisticated vehicle that they could fly back and land on Earth from space. The lifting body idea was unusual because the vehicle didn't have any wings. The shape of its body alone had sufficient lift to fly. Despite favorable research on lifting bodies, there was little support for a flight program at NASA headquarters. Engineer Dale Reed decided that a flight demonstration was needed before wingless aircraft could be taken seriously. So, in February 1962, he built a model lifting body and launched it from a radio-controlled mothership in his backyard. While Dale flew the model, his wife took home movies of these flights, which helped Reed convince his boss to give the go-ahead for the construction of a full-scale version. But they would have to build it without funding support from NASA headquarters.
There was very little confidence among NASA headquarters planners of spacecraft missions in the lifting body concept. It was strictly a theory and an idea that a few technical people had. We flight test people felt that if we were to fly one of these and demonstrate that they can fly, then they would be the lifting body would be considered for future designs for future spacecraft.
NASA craftsmen and engineers took on the task and began building this new vehicle that they dubbed the M2F1. It was built with a tubular steel interior frame and a mahogany plywood shell.
We did this on an informal basis. I was allowed to select my team of engineers and technicians that had experience in building home-built airplanes. And we proceeded with the design and construction of the vehicle in that fashion.
Once the vehicle was done, Reed and other engineers towed the M2F1 across the desert runway with a souped-up Pontiac convertible. On April 5, 1963, pilot Milt Thompson lifted the M2F1's nose off the ground for the first time, proving the lifting body concept. Later tests were done with a NASA C-47 that lifted the M2F1 to about 12,000 feet and released it. The lifting body dove toward the ground at 150 miles per hour, but the landing was smooth and the lifting body program was on its way.
That was probably the most exciting thing in my career, with Milt Thompson being released at 12,000 feet, doing a successful flare out of a very steep approach and coming very softly on the lake bed. I feel very proud of the fact that we accomplished a very major milestone in history by demonstrating an airplane that can fly without wings and that can be applied to exciting designs of the future, especially in the spacecraft field.
More than 400 ground tows and over 100 aircraft tow flights were carried out on the M2F1. The lifting body research was used heavily in the design of the space shuttle and is still being used today to design new vehicles like the X-38. The lifting body program has proven to be one of the most valuable programs in NASA history.
So mga ka-spacers, isn't that fascinating about the lifting body aircraft? The lifting body aircraft eventually led to the development of the space shuttle. So, at this point, mga ka-spacers, let us now identify some of the major components of the space shuttle. Now, the space shuttle components includes the orbiter vehicle or OV with 3 clustered Rocketdyne RS-25 main engines, a pair of recoverable solid rocket boosters or SRBs, and the expendable external tank or ET containing liquid hydrogen and liquid oxygen. The space shuttle was launched vertically like a conventional rocket, with the 2 solid rocket boosters operating in parallel with the orbiter's 3 main engines, which were fueled from the external tank. The SRBs were jettisoned before the vehicle reached orbit, and the external tank was jettisoned just before orbit insertion. So those are the major components of the space shuttle. So at this point, let us now zoom in on the space shuttle's orbiter. Now, the orbiter resembles that of a conventional aircraft, and the orbiter's main function is to accommodate and to carry astronauts and payloads. The space shuttle's main engines are also mounted on the orbiter, and as I have mentioned a while ago, there are 3 Rocketdyne RS-25 engines that are mounted on the orbiter, and the entire body of the orbiter is made from aluminum alloy. So that's the orbiter of the space shuttle that resembles that of a conventional aircraft, and the orbiter has 3 Rocketdyne RS-25 engines. And what's so special about the orbiter is that it has a robotic arm, commonly called as the Canadarm. Now, the Canadarm of the space shuttle is a series of robotic arms that were used on the space shuttle orbiters to deploy, maneuver, and to capture payloads. Now, aside from the Canadarm of the orbiter, the Space Shuttle orbiter is also equipped with a heat shield. The Space Shuttle's heat shield is also known as the Thermal Protection System, or TPS, or heat shield. The heat shield is a barrier that protected the Space Shuttle orbiter during the searing 1,650 degrees Celsius or 3,000 degrees Fahrenheit of heat during atmospheric re-entry. Another important goal of the heat shield was to protect the Space Shuttle orbiter from the heat and cold of space while in orbit. The heat shield or the thermal protection system is composed of heat tiles that surrounds the Space Shuttle. So mga ka-spacers, the thermal protection system of the Space Shuttle is composed of these thermal tiles as you see in this picture. These thermal tiles protects the Space Shuttle from extreme heat during re-entry. Now, the thermal protection system is composed of 4 types of tiles. The nose cone and leading edges of the wings of the orbiter experiences temperatures above 1,300 degrees Celsius, or that's about 2,300 degrees Fahrenheit of heat, and were protected by reinforced carbon-to-carbon tiles or RCC. Thicker RCC tiles were developed and installed in 1998 to prevent damage from micrometeoroid and orbital debris, and was further improved after RCC damage caused in the Columbia disaster. Beginning with STS-114, orbiter vehicles were equipped with the wing leading edge impact detection system to alert the crew of any potential damage. The entire underside of the orbiter, as well as the other hottest surfaces, were protected with high temperature reusable surface insulation. So that's the thermal protection system of the Space Shuttle orbiter. So mga ka-spacers, here is a picture of the Space Shuttle Discovery's thermal protection tiles. These thermal protection tiles protects the orbiter from extreme heat during re-entry. Alright, now what about the so-called orbiter payload bay? Now, the orbiter payload bay comprises most of the orbiter vehicle's fuselage and provided the cargo carrying space for the Space Shuttle's payloads. It was 18 meters or 60 feet long and 4.6 meters or 15 feet wide, and could accommodate cylindrical payloads up to 4.6 meters or 15 feet in diameter. Then 2 payload bay doors hinge on either side of the bay and provided a relatively airtight seal to protect payloads from heating during launch and re-entry. So that's the orbiter payload bay. Now, what about the external fuel tank of the Space Shuttle? Now, the function of the external fuel tank is to supply liquid oxygen and hydrogen to the main engines. And the external fuel tank also acts as a backbone to vehicle, providing attachment to the solid rocket boosters and the orbiter. So, like what I have mentioned, the external fuel tank provided the propellant to the Space Shuttle's main engines from liftoff until main engine cutoff. Eventually, the external tank separates from the orbiter vehicle 18 seconds after engine cutoff, and this could be triggered automatically or manually. Eventually, the external fuel tank returns to Earth and drops at either the Indian Ocean or the Pacific Ocean. And mga ka-spacers, the external fuel tank was the only major component of the Space Shuttle that was not reused and could travel along a ballistic trajectory either, as I have mentioned, in the Indian Ocean or the Pacific Ocean. So that's the external fuel tank of the Space Shuttle. So mga ka-spacers, another vital component of the Space Shuttle are the so-called solid rocket boosters. The solid rocket boosters, or SRB, provided 71.4% of the Space Shuttle's thrust during liftoff and ascent, and were considered the largest solid propellant motors ever flown. So isn't that fascinating, mga ka-spacers? And the SRBs were jettisoned 2 minutes after launch, as seen in this photo. And eventually, the SRBs are retrieved and prepped up for the next mission. So isn't that fascinating, mga ka-spacers? Alright, so let's take a look now at a typical mission profile of the Space Shuttle. Now, a typical shuttle mission lasts 7 to 8 days, but it can extend to as much as 14 days, depending upon the objectives of the mission. A typical shuttle mission is as follows. You have the launch, ascent, orbital maneuvering burn, orbital life in space, re-entry, and landing. So let's take a look at the launch sequence of the Space Shuttle. So the Space Shuttle is launched from Kennedy Space Center. And T-minus 31 seconds, the onboard computers takes over the launch sequence. And then T-minus 16 seconds, sound suppression water system is activated. Then T-minus 6.6 seconds, the shuttle's main engine ignites. And T-minus 3 seconds, shuttle main engines are in liftoff position. And T-minus 0 seconds, the SRBs are ignited and the shuttle lifts off. So mga ka-spacers, so isn't that fascinating and jaw-dropping na nandyan kayo sa Kennedy Space Center at makapanood man lang ng isang shuttle launch? Diba? Talagang mamamangha kayo at tutulo ang laway ninyo na mapanood nyo man lang yung space shuttle na umalis sa kanyang launch pad at lumipad patungo sa kalawakan. Diba ang ganda at nakakamangha talaga? Kung ako nga po, mga ka-spacers, yan ang pangarap ko sa buhay na talagang gusto kong pumunta sa Kennedy Space Center at makapanood man lang ng isang shuttle launch. At kung matupad ko man lang yan, pwede na akong mamatay sa mundong ibabaw. And kahit na yung SpaceX man lang, makapunta lang ako sa Kennedy Space Center and makapanood ng SpaceX launch, pwedeng-pwede na po ako. Alright, so that's how fascinating mga ka-spacers ang launch ng Space Shuttle at T-0 seconds. Okay, then at T plus 20 seconds, the shuttle begins a combined roll, pitch, and yaw maneuver to orient the vehicle to correct orbit. Then at T plus 60 seconds, the shuttle engines are at maximum throttle. Then eventually, the SRBs would be jettisoned, maghihiwalay na yung dalawang SRBs. And then, upon reaching orbital velocities, the external fuel tank separates from the orbiter, and then eventually the orbiter reaches orbital speed. So, isn't that fascinating, mga ka-spacers?
This is the orbiter vehicle, the part that looks like an airplane and carries the astronauts and payloads into space. It takes so much fuel to get into space that we need a really big gas tank. That's what the orange external tank is for. It provides the fuel for the 3 space shuttle main engines. Even this isn't enough to launch us into space. We need 2 extra rockets on each side. These are called the solid rocket boosters, or SRBs. It takes a lot of work to get all of these pieces ready for the launch. There were 2 launch sites for the space shuttle: Kennedy Space Center in Florida and Vandenberg Air Force Base in California. Shuttle launches from the Vandenberg site ended up being canceled, and as a result, all 135 shuttle missions were launched out of Florida. So let's take a closer look at Kennedy Space Center in Florida. It has 2 launch pads, 39A and 39B. Shuttle missions were launched from both of these pads. There's a few buildings way over here, about 5 kilometers away from the pads. The large one here is the Vehicle Assembly Building, or VAB. It's as tall as a 38-story building. This is where they would assemble the space shuttle in preparation for a launch. Next to it is the Launch Control Center. Notice how it's positioned with a good view of both launch pads. This building is called the Orbiter Processing Facility, or OPF, and actually there were 3 OPF buildings. It's where the orbiter was serviced in between missions. Over here is the Shuttle Landing Facility. This is where a mission ends for the space shuttle. But they didn't always land here. Sometimes, due to weather or other circumstances, the shuttle would land in California at Edwards Air Force Base. When this happened, we need to get the orbiter vehicle all the way back to Florida, and the shuttle can't really take off again and fly like an airplane. It wasn't built for that. So here's what happened. The orbiter vehicle was taken to the Mate-Demate device, or MDD, which would lift up the shuttle and then load it on the back of a special airplane called the Shuttle Carrier Aircraft. It was then flown across the United States to get back to Kennedy Space Center in Florida. It was then taken to one of the OPFs. Once inside, the engineers would literally crawl all over it to fix or replace many of the shuttle components to make sure that it's safe to fly for the next shuttle mission. This process can take several months to complete. This is part of the reason why the space shuttle was so expensive. Meanwhile, work starts over here at the VAB. We start with the solid rocket boosters, which are assembled piece by piece. On the inside is the solid rocket fuel. Once ignition starts at liftoff, it cannot be turned off. Now it's time to lift the external tank into place. Inside, there are 2 smaller tanks, one for liquid hydrogen and one for liquid oxygen. These tanks will remain empty until just a few hours before the launch. Now at room temperature, hydrogen and oxygen are both gases which take up an enormous amount of space. But if we put them at extremely cold temperatures, they will turn into liquids and we can put a lot more fuel inside of the tanks. The liquids from each tank will flow through pipes down to where it will connect to the orbiter. This side is for the liquid hydrogen, and this side is for the liquid oxygen. Once the orbiter was ready, it was then transferred from the OPF to the VAB. This was referred to as a rollover. The orbiter was then hooked up to a crane and then carefully lifted up, moved over to the high bay, and then mounted to the side of the external tank. The fuel and electrical connections are attached to the bottom of the orbiter. There is also another attachment point up towards the top. Once this is all ready to go, we need to move it to one of the launch pads, which are more than 5 kilometers away. This is referred to as the rollout. The weight of the entire shuttle stack is supported at the base by 8 hold-down posts, 4 on each of the SRBs. It's then secured in place by the hold-down bolts. At the moment of liftoff, these will detonate to free the shuttle. The platform it's on is called the Mobile Launch Platform. Underneath is the crawler transporter, which moves everything at just under 1.5 kilometers per hour. It takes many hours to get all the way to one of the 2 launch pads. Then it's up the ramp and slowly into position. The platform is put down on supports, and the crawler goes back down the ramp. The mobile launch platform has large holes for the rocket flames. The 3 main engine flames will go through this hole, and the flames from the 2 SRBs will go through these 2 holes. Below the pad is the flame trench. During the liftoff, the flames will be deflected to each side. The structure next to the shuttle stack has 2 main parts: the fixed service structure, which doesn't move, and the rotating service structure, which can pivot around to completely enclose the space shuttle. Sometimes the payloads were loaded here in the vertical position, and other times they were loaded before this, when the orbiter was on the ground at the OPF. The fixed service structure has a lightning mast on top, and then 3 service arms. 2 of them are vent arms, which will collect excess hydrogen and oxygen from the external tank. This is the gaseous hydrogen vent arm, with the ground umbilical carrier plate at the very end. At the top is the gaseous oxygen vent arm. Because the fuels are so cold, the beanie cap is really important to prevent ice buildup at the very top. The third arm is called the orbiter access arm. At the end of it is the white room. This is how the astronauts get on board the orbiter in preparation for a launch. Down here are the 2 tail service masts. They have connections to each side of the orbiter. On the day of the launch, this is where the fuel will come in to fill the orange external tank. If there is an emergency on the launch pad and the astronauts need to get away in a hurry, they will come over here to the emergency egress system. It has several baskets that can quickly carry them far away from the launch tower. Each basket can hold 3 people. One more feature of the mobile launch platform is the sound suppression system. Beginning at just a few seconds before launch, water will start pouring out from a few different places. This will limit the sound shockwaves from bouncing back up and damaging parts of the space shuttle as it leaves the ground. The water is stored in this large tower on the launch pad. So let's see how this works on the day of the launch. There are many things that have to happen in order. I can't cover them all in this video, but let me show you some of the main ones. At T-minus 5 hours and 35 minutes before the launch, fuel begins loading into the external tank. The fuel comes from the white spherical tanks on the edges of the launch pad. Remember that the SRBs already have their solid fuel inside of them. At T-minus 3 hours, the astronauts leave for the launch pad and begin to enter the orbiter vehicle. Since the shuttle is vertical on the launch pad, all of the seats are in the laid-back position. Most missions had 7 astronauts, 3 in the middeck and 4 in the flight deck. There are no windows on the middeck, so some of the astronauts won't be able to enjoy the view on the way up. There's a lot of excitement coming up to the moment of liftoff. However, if there are any problems such as mechanical failures or even bad weather, then the launch will be delayed or even cancelled until another day. This is called a launch scrub, and it can happen all the way up until just a few seconds before liftoff. At T-minus 7 minutes and 30 seconds, the orbiter access arm is slowly retracted. If there is an emergency, they can quickly bring it back into place. At T-minus 3 minutes and 45 seconds, main engine gimbal tests to make sure that it's working correctly. T-minus 2 minutes and 55 seconds, the beanie cap is lifted and the gaseous oxygen vent arm is retracted. At T-minus 10 seconds, activate the hydrogen burn-off system. And no, this does not actually start the engines. That happens up here inside of the combustion chamber. What these sparks do is ignite any excess hydrogen. This hydrogen can cause an unexpected explosion at launch if it isn't taken care of. At T-minus 6.6 seconds, the 3 main engines ignite. All 3 of them must work correctly or they will shut down and abort the launch. At the moment of liftoff, many things happen simultaneously. The gaseous hydrogen vent arm is retracted from the external tank. The 2 connections at the tail service mast will retract. The 8 hold-down bolts will detonate, which frees the shuttle, and then both SRBs ignite. For their journey into space, the shuttle is mostly flown by the autopilot. Of course, the astronauts can still take over if they need to. Shortly after clearing the tower, they do what's called the roll program, to get the shuttle so that it's heads down for most of the ascent into space. This reduces the aerodynamic stress on the wings. It will also allow the astronauts to see the curve of the Earth as they ascend into space. Now, as we keep gaining more and more speed, the air in the atmosphere will create pressure on the front of the spacecraft. Then as we get higher, the air starts to thin out. They use the term max Q to refer to the time when the aerodynamic pressure will be at its highest. During max Q, the main engines will be throttled down, so we don't accelerate too quickly, but then shortly after, we can throttle them back up again. A little more than 2 minutes after liftoff, the 2 SRBs have done their job. They are detached, and then small rocket motors on the bottom and on the top fire on each booster to ensure that they are separated from the vehicle. The SRBs fall back down to the Earth where they will parachute in for a soft landing in the ocean. They will be recovered by boat and then refurbished for a future shuttle mission. Now the 3 main engines are on their own. As we get higher, more and more fuel will be used up from the external tank. This means that the shuttle will keep getting lighter. We have to keep throttling down the engines or we'll accelerate too quickly. The maximum amount of acceleration we want the astronauts to feel is 3 Gs, or 3 times the force of gravity pushing them into their seats. At about 8 minutes and 30 seconds, we have main engine cutoff, or MECO. This must happen before the tanks run dry so that the engines aren't damaged. The external tank is now detached. We're not in orbit yet, so the tank will head back down to Earth and burn up in the atmosphere. The 2 doors on the bottom side of the shuttle will close now that the external tank is gone. If they didn't close, we would have gaps in the heat shield at the end of a mission, which would not be so good. At this point, the orbiter vehicle is on the same path as the external tank. We're not quite going fast enough to stay in orbit around the Earth. Remember that the external tank had the fuel for the 3 Space Shuttle main engines, so we can't really use these anymore. Instead, we'll use the 2 OMS rocket motors. These each carry their own fuel inside of the pod here. This gives us that last push into orbit around the Earth. Now it's traveling at 28,000 kilometers per hour, many times faster than the speed of a bullet. Now it's time to do some science, release a satellite, or dock to the International Space Station.
Now, once the shuttle is in orbit, the astronauts can stay inside the shuttle for at least 7 to 8 days. But it can extend to 14 days depending on the parameters of their mission. And once the mission is accomplished, the astronauts can now prepare for re-entry. Now, re-entry is usually done under computer control, but the astronauts can prepare manual re-entry if an emergency arose. Usually, re-entry begins by firing its OMS or Orbital Maneuvering System engines, and the orbiter flies in the opposite direction to orbital motion for approximately 3 minutes. This will slow down the space shuttle, and eventually the space shuttle will return to the Earth's atmosphere. So here is a photo of the OMS engines or the Orbital Maneuvering System engines that will be activated to slow down the space shuttle to suborbital speeds. Eventually, the shuttle returns to the Earth's atmosphere, encountering friction, and eventually the shuttle heats up. But again, as I have mentioned, the shuttle is protected by its thermal protection system tiles. Then, eventually, the space shuttle now glides to the Earth's atmosphere like a brick. So they call this now the flying brick without any power at all, like a glider. And eventually, the shuttle lands and deploys its parachute to slow down its motion. So, isn't that fascinating indeed? That's the re-entry and the landing of the space shuttle.
Sonic booms announcing Discovery's arrival. It's now just 68 miles away from Kennedy Space Center, 27,000 feet in altitude, and traveling 530 miles per hour.
Discovery on at the 180.
On at the 180.
Pilot Jim Dutton now taking over controls of the shuttle for a moment. That call from Capcom Rick Sturko indicates the shuttle has 180 degrees to go in its turn around toward runway 33. All continuing to look good on board Discovery as it makes its way home. 68 miles to go, currently 3 miles in altitude, and traveling 420 miles per hour.
Discovery, you are on at the 90.
On at the 90.
And Commander Alan Poindexter now back in control of Space Shuttle Discovery. Just 2 minutes now until touchdown.
Houston Discovery, runway in sight.
Roger.
Less than a minute and a half until touchdown. Discovery is now descending at a rate 20 times higher and 7 times steeper than what a commercial airline would experience on its final approach. One minute now until touchdown. Discovery's landing gear will be locked down and into place at 300 feet in altitude. It's currently 3,500 feet and traveling at a rate of 370 miles per hour. "30 seconds until touchdown. Main gear, landing gear now down and locked. Main gear touchdown. Pilot Jim Dutton now deploying the drag chute. Nose gear touchdown. That brings an end to the STS-131 mission, the 131st Space Shuttle flight, and the 33rd to the International Space Station. Discovery left Florida on April 5th with 7.6 tons of new science equipment and spare parts, including equipment that should improve the station's capability for Earth observation work, equipment that could help astronauts avoid muscle atrophy and scientists better understand muscle atrophy, and equipment that will help keep the station systems cooling properly. Discovery brings home with it the last large return load from the station, 2 tons of used equipment.
Roger, wheel stop Discovery. Welcome home. Dex, congratulations to you and the crew on an outstanding mission. There are no immediate post-landing deltas. We'll meet you on page 5-3 of the entry checklist.
Houston Discovery, thanks for those words, CJ. It was a great mission. We enjoyed it. We enjoyed working with you and all the teams in mission control. And we're glad that the International Space Station is stocked up again. Thanks a lot.
So mga ka-spacers, let us now identify the names of the different space shuttle orbiters according to the order in which they were built. So first we have the Enterprise, the Space Shuttle Columbia, the Space Shuttle Challenger, the Space Shuttle Discovery, the Space Shuttle Atlantis, and the Space Shuttle Endeavour. The Space Shuttle Enterprise was flown only within the Earth's atmosphere during shuttle approach and landing tests conducted in 1977. It was never flown in orbit. But mga ka-spacers, the Space Shuttle Enterprise was named after that famous starship from the hit TV series Star Trek. See, so to boldly go where no man has gone before. That was the vision behind the space shuttle, to boldly go where no man has gone before. But in spite of that, there were some unfortunate disasters involved in the space shuttle. So first we have the Challenger disaster and we have the Columbia disaster. And because of those disasters, plus the fact that there are financial constraints in the launch of the space shuttle, eventually the space shuttle was decommissioned. The space shuttle retirement was announced in January of 2004. President George W. Bush announced his vision for space exploration, which called for the retirement of the space shuttle once it completed the construction of the ISS. So that ends the remarkable era of the space shuttle. So mga ka-spacers, I hope you have learned a lot about the space shuttle, its history, development, its missions, the disasters, and the reason for its decommission. So, thank you for watching. Thank you sa inyong pagtutok sa ating programang Space, the Final Frontier. So, marami pong salamat sa inyong pagtutok. Shout out sa mga students ko from 11 and 12 STEM. Shout out din po sa mga officers and crew of the BEDAN Society of Young Astronomers, and shout out din po sa mga administrators ng San Beda University Senior High School. And shout out sa mga suki natin out there, mga ka-spacers na walang sawang nakatutok sa ating programang Space, the Final Frontier. So I guess that's all for tonight. Marami pong salamat. This is your Ka-Spacers and Space Commander Professor Jun Cajigal saying, live long and prosper. And I will see you mga Ka-Spacers in our next episode of Space, the Final Frontier. Always stay safe and goodbye everybody. See you in our next episode.
NASA's Voyager 1. Launched in 1977.
But that's just very small potatoes compared to what the Earth is involved with and knows about.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
One small step for man, one giant leap for mankind.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.